Hello again. We're driving on with ME4111, Engineering Mechanics 1 Statics. We're working through tutorial sheet 5, and we're currently on question 5. So you can see now the questions are starting to get a bit more complex in terms of what they're asking. So this is typical of all the tutorial sheets, that they start a bit easy and then get a bit more tricky. Hopefully, as you develop through them. So if we look at this one, we're asked to calculate the reactions at the bolted base O, so down here, of this traffic light assembly. Each traffic light module, so that's this thing, has a mass of 36 kg. And the masses of OC is this thing here, there to there, that's 50 kg. So we'll have 50 kg acting at the center point of that. And A to C, which is from here to there, is 55. Oh, yeah, it's written there, 55. And yeah, it's acting at G. Okay, so that's the mass center of that there, 1 meter off from one of the traffic light modules. Okay, so our procedure is pretty standard at this stage. You should be familiar with it, that we opt for a free body diagram. Okay, so as I say in the cookery shows, here's one I prepared earlier. With the outline of our structure, I'm not showing the ground. So again, if I just flick back, we have this ground here with the grass, not shown. Okay, so I just have the structure and then I apply the loads. So the obvious loads are obviously the weight of the modules. So WA, WB, the weight of this part of it here. So the structure AC, that is acting there. So I have WAC for that. And then we have this beam here, and the weight of that acting there at the midpoint of that. Okay, so that's WOC. All right. Then, excuse me, down here we have our reaction forces. I'll just clear that. And it's a fixed support into the ground that you can see. Okay, so it's the bolted base O, so it's bolted into the ground. The idea is that this thing doesn't move. So that means that it can support a vertical reaction in the Y direction, a horizontal reaction in the X direction, and also support a moment. So it's designed to resist rotation. So again, the way to think about that, if you're not sure, is make a cut here and try and push this into the ground. Ignore the stuff that's going on up there. And if you try and push into the ground, obviously it's going to push back, it's going to react. Okay, so that's that. And then if you try and push it in this direction or this direction, so there are two directions of motion, you'd expect it to resist that. And then if you try and twist it, either this way or twist it that way, again, you expect it to react to that. It's bolted in, it's going to resist that motion. So that's why we have the two force reactions here, one in the X, one in the Y, and then we have the rotation reaction as well. And as shown, that's going in an anti-clockwise rotation, so that would be a positive moment. Okay, so that's my free body diagram. Again, I've just highlighted it up there, FBD, and I've written in some of the dimensions that I need, because what I want to do now is I want to forget about this, no longer look at that, and I just want to base my solution off this. Okay, so the dimensions there help me out. All right, so I've left that in because that's how I'm the basis for producing these equations, and the system is in equilibrium. So I have my three sets of equations. Some of the forces in X equals 0, some of the forces in the Y direction equals 0, and moments about any point whatsoever equals 0. Right. So some of the forces in X equals 0. The only one acting in X is my OX. So this one here. All right. So OX equals 0. In the Y direction, then I have minus WA, minus WB, minus WAC. So this one, this one, this one. I have WOC, which is in here, so don't forget about that. And I have OY. So plus OY, given the way I've drawn it there, equals 0. So actually OY comes straight out of that, 1736.4 newtons. Okay, so that's straightforward enough. I want the moment reaction also. So I have OX, I have OY, but I also want the moment reaction because I was asked for the reactions. calculate their reactions. Okay, I didn't say force, it said their reactions. And this moment is a reaction. So I need that also. And taking moments will give me that. So I'm going to pick moments about 0.0. And that would knock out any moments due to these two forces here. And I'll just have moments due to this one, this one, and this one. This one is also going to be knocked out. I'll go back to the previous one, this one here. The line of action of this goes through 0.0. So again, it will have no turning effect about 0.0. So if I take moments about here, I've knocked 3 forces out of it. And I'm left with 3 forces of the 6. All right, so that's a clever place to take moments. So taking moments about 0.0, I have 36 times 9.81 times 10. So 5 plus 1 plus 4 is the distance from WA, the line of action of WA over to 0.0. Again, I'm given that a plus because if I look at this one will swing it down in an anti-clockwise direction. So just WA about 0.0. That gives me a plus on that. Likewise, WB. The distance now is the same mass, gravity 9.81, and now my distance is 5, 1 plus 4. I have the 55 kilograms on this one here. Again, sorry, the 55 kilograms, so times 9.81. The distance now is 4 meters. And again, it's going to swing it in an anti-clockwise direction. So again, that becomes plus there. Okay, so my distance, sorry, my plus or minus on these, I'll just write plus there explicitly. I tend to do it. I just forgot to do it in this one. Obviously, you don't have to with the plus, but I like to do it just to be explicit about it. So we have plus on all of these because of the direction of rotation, nothing to do with the, if you look at these are all pointing in a negative y direction, so don't write a minus because of that. Okay. And the last one then is m naught, which I've drawn going in an anti-clockwise direction, so that is also positive by my convention. So all those moments sum to 0. Okay. So I know that, I know that, I know that. So this means I can solve for m naught. And that gives me m naught as minus 7455.6 Newton meters. Okay. Now the minus in this, what does that mean? The minus in this means that the direction of this moment is opposite to the way I've drawn it in the free body diagram. So in my free body diagram, let's change color here. I've drawn this going in the anti-clockwise direction. So by getting a minus for the answer, it means it's going in a clockwise direction. All right. So it doesn't mean that it's minus in terms of the direction. It is relative to how I drew it in the free body diagram. Okay, and if you look at it, like all of these things are swinging in an anti-clockwise direction. So at this moment, got to be swinging the other way to cancel those out for equilibrium. All right. So that gives us a clockwise direction. So that minus sign there is the alert that in my free body diagram, I've just drawn that the wrong way around. It's actually pointing the other way. So your answer is always referenced back to your free body diagram and not to the coordinate system. Okay, so to the free body diagram. So just bear that in mind. Okay, that concludes that. And we'll drive on with the other ones and hopefully I'll get those up in the next couple of days. Talk to you soon.